Welcome to our second lecture on underground cable. In the last lecture, we have discussed the geometry or construction of the underground cable, its advantage, its disadvantage, and we have seen the insulation resistance of the underground cable. It varies inversely with the length of the underground cable. In today's lecture, mainly or this part of this lecture on underground cable, we shall mainly focus on what is the capacitance of the underground cable, which is very significant. Inductance is not that much of significant in case of underground cable. What is the capacitance of the underground cable, and in addition to that, we shall see what will be the electric stress on the conductor or in the dielectric interface, that is the variation of electric stress. So let us proceed to our topic. So we shall see two aspects in this part of this on lecture on this underground cable. That is, what is the capacitance of underground cable of single core. That means single core means we have one conductor. And second aspect, variation of electric stress of electric stress. Now, capacitance of the underground cable is given by this formula. 2 pi, in the numerator we have 2 pi epsilon 0 epsilon r, and in the denominator we have ln d by r. What is d and r? As I told you, to analyze underground cable electrically, we require only two layers. That is, first layer is the conductor, that is which is called core, and second layer is called sheath. But this much only, core and sheath. Core having radius r and sheath having radius d. Line voltage is impressed on core or the conductor, and sheath is supposed to or expected to be grounded. Okay, now to understand or to derive this formula, we shall assume similar kind of figure. That means we shall consider a thin circular element of thickness dx. Let us say this should be, or this is a thin element of thickness dx, and it is situated at a distance of x. So we shall first evaluate electric flux density dx. What is dx? Dx is equal to, that is charge q by 2 pi epsilon 0, not epsilon 0 this time, 2 pi x into 1. 2 pi x into 1. Why 1? Because we have considered only cross-sectional view, so height becomes 1. Height becomes 1 in this case. So geometrically, because this is nothing but a coaxial cylinder. Geometrically, this is nothing but a coaxial cylinder having height 1, so its area becomes 2 pi x. X is the radius. So circumferential area becomes 2 pi x into 1. So now electric stress at distance x, electric stress at x, we have Ex, that will be equal to dx by epsilon. So it will be q by 2 pi epsilon 0 epsilon r into x. So we have potential difference V, we have potential difference V, which is equal to minus Ex integration Ex into dx. So integration should be carried out from capital D to small r, from the definition of the potential. So as the reverses, as the limit reverses, this minus, so minus sign goes away, goes off. So it will be q by it will be q by 2 pi epsilon naught epsilon r into integration small r to capital D dx by x. So V is equal to q by 2 pi epsilon 0 epsilon r ln d by r. So this is the potential difference for you. So later on we shall use this formula. So let me square it up. Later on, in a moment, we shall use this formula. Okay, now what will be the capacitance? So capacitance is equal to capacitance C, that will be equal to charge per voltage. So it should be q by V, from this expression should be 2 pi epsilon 0 epsilon r by ln d by r. Now the unit of this capacitance as derived in this formula, not in microfarad, but it will be microfarad per meter. Why? Because from the diagram itself, as I told you, the diagram is considered here is per unit length. Okay, the height becomes 1, so the unit should be also microfarad per meter. So this is the capacitance of single core cable, 2 pi epsilon 0 epsilon r divided by ln d by r. So now we shall proceed to our next topic or next aspect, which is the electric stress. That is the variation of E. Okay, so this is the next part. So we start with this formula. We start with this expression with this formula. What we have? We have Ex, which is equal to q by 2 pi epsilon 0 epsilon r into 1 by x. This much we have. So now we want to utilize this formula or this expression here. What is q by 2 pi epsilon 0 epsilon r? So from this expression we can write Ex, which is equal to, now q q by 2 pi epsilon 0 epsilon r, which is equal to v by ln d by r 1 by x. So in place of q by 2 pi epsilon 0 epsilon r, from this equation, let us say this is equation 1. So from equation 1, we have substituted q by 2 pi epsilon 0 epsilon r is equal to v by ln d by r. So from there we can write x, which is equal to v by x ln d by r, which is a very important relation. Now we shall plot the variation and see what is the variation. So let us say we have E along y-axis and x along x-axis. So this is x, and we have along y-axis we have Ex. Now we have at x equal to r. That means we are at conductor surface. So E on the conductor, which is equal to v by small r into ln capital D by small r. So let us say, so we have at this place x equal to small r. That means we are at conductor surface, and this value is v by small r ln d by, so this value, this electric stress, this value of electric stress occur on the conductor surface. On the other hand, at x equal to capital D, that means we are at dielectric surface. We are at dielectric surface. So that value should be is equal to v by, now in place of x we should write d ln d by r. So let us say at this place we have x equal to d. We have, that means we are at dielectric surface. Let us say this is the value. So this value should be v by capital D ln d by small r. Now as you can see, this Ex is, as you can see, Ex, that is variation of electric field, is inversely proportional to the x. That means it roughly follows rectangular hyperbolic nature. So this nature or electric variation should not be linear, so it is following a roughly rectangular hyperbolic nature. So this curve of variation of electric field is important. What we can conclude from here? Maximum stress on the conductor surface, minimum stress on the dielectric, and the variation is rectangular hyperbolic. Rectangular hyperbolic. Okay, so in addition to this, we shall see maximum stress occurs on conductor surface. So mathematically or numerically it is equal to, it is E is equal to v by small r ln d by small r. That's right. Now, in order to minimize E, in order to minimize stress on the conductor surface. So what is the way? You see, this V is constant, you cannot alter. So in order to minimize the conductor stress, one only is to increase or is to maximize. Okay, maximize this denominator. So maximize this denominator. Now to maximize R over ln d by R, what should we do? We should take this. We should take derivative of this term R ln d by R, and we should make it is equal to 0. So if we can able to do that, we will see a definite relation for which this term, for which we shall see a definite relation. We shall see a definite relation for which we will have this term is maximum. Okay. So now let us find out what is that relation. So from there, from this result, we can have DDR of minus R ln R, which is equal to 0. Now if you take the derivative of first term, it is become only ln D, then minus. Now if you take the derivative of R as ln R constant, so it will be only ln R, and next we will have R into 1 by R, that should be equal to 0. Now with these two terms, again we have got one term ln d by R, and with this we will have 1 at right hand side. So we will have a very significant relation, that is d by R is equal to E, which is equal to 2.718. It is a very important relation. What does it mean? It says that if the ratio between D and R is maintained at 2.718, okay, if the ratio between D and R is maintained at 2.718, at that condition our electric stress on the conductor surface will always be minimum, and this condition is called optimum cable geometry condition. Optimum cable geometry. So if we maintain this ratio, if we maintain this ratio, then our stress on the conductor will be always minimum, So with this I am stopping this part. So in this lecture, what we have seen, or what we have gone through, that firstly we have seen capacitance of underground cable, one core single core cable. We have got a formula, C is equal to 2 pi epsilon 0 epsilon r divided by ln d by R, which is surprisingly quite similar with that of overhead line capacitance calculation. Secondly, we have seen electric stress variation follows rectangular hyperbolically. Maximum value of E occurs on the conductor surface and minimum value of E occurs on the dielectric. However, there should be a relation in design purpose, that is D and R, so that the electric stress that occurs on the conductor surface should be minimum, and that is roughly is equal to D by R, see 2.718. So if we maintain this relation or this ratio, electric stress on the conductor surface is expected to occur at least value. So with this, I am ending here. In the next part of this lecture, we shall see more topics. Okay, thank you.